The Euler's sum of degrees theorem. That's what we were talking about at the very end last time. I just had a couple more things to say about that, and then we'll move on to something completely different. But this is one of the items on our big list. This is Euler's sum of degrees theorem. All right. And I will just remind us of what it says. It's a very strange, in my opinion, a strange theorem which applies to a lot of real life situations although it's always kind of mysterious in my mind, the sum of degrees theorem. It says there's kind of two different ways to say it. So maybe I'll put two little bullets here. It says the total sum of degrees in any graph is always even. This is the sum of degrees theorem. The total sum of the degrees, I just mean if you look at a graph and you find the degrees of every vertex and you add them all up, the total sum must be even. For example, I'm just going to make something up here. How about that? Missed this vertex over here. How about this as a graph? What are the degrees? I hope everybody remembers the degree is just how many edges touch each vertex. So that's a 2, that's a 3, that's a 3, that's a 3, that's a 1. All right. And in this example, what is the sum of the degrees? I would add 3 plus 3 plus 3 plus 2 plus 1. That's 12. The sum here would be 3 plus 3 plus 3 plus 2 plus 1, which I believe is 12. And of course, 12 is an even number. And so this graph demonstrates the Euler sum of degrees theorem. This, of course, is only one graph I'm showing you. But the sum of degrees theorem says that no matter what the graph looks like, the total sum of all the degrees is always even. And another way of saying the same thing, which kind of looks different, but these two things are equivalent, is another way to say it is the number of odd degree vertices is always even. That's because when you add up a bunch of numbers, if you add a bunch of numbers and the answer is even, it means that there must have been an odd number of odds. That's because if you are adding up numbers, some of which are odd and some are even, if you have an odd number of odds, they add up to an odd. If you want it to add up to an even, there has to be an even number of odds. Is that what I said? I think I said it backwards. If you want it to add up to an even number, there has to be an even number of odds. That's why these two things are actually equivalent, even though they look different. The number of odd degree vertices in any graph is always even. All right? This is the sum of degrees theorem. So something that I didn't mention last time is that is just why this is true. And actually the reason why this is true is fairly straightforward. If you think about adding up the sum of degrees, like in this graph over here, you have to remember what the degree means. The degree means it's how many edges meet this vertex. So there's a 3 here, which is because there's 3 edges right here. There's a 3 here because there's 3 edges like that, right? But if you think about what the sum of degrees represents, I would say it this way. Every edge contributes. This is actually, would you mind me saying? This is a proof, although it's very simple once you look at it in the right way. A proof of why the sum of degrees theorem is true. Every edge contributes 2 to this sum. That's because every edge has 2 ends to it. So for instance, if I look just at that edge right there, what I mean by it contributes 2, I just mean like this 3 over here, one of those 3 is because of this edge, and one of those 3 is because of this edge. So this edge, in terms of the total sum of degrees, that edge is responsible for 2 of them. There's this end and this end. So this edge is responsible for contributing 2 to the total sum. And this is true of every edge in this graph adds 2 more to the total sum of the degrees. In fact, what that means is, The sum of degrees, actually this, I didn't say this, but this is also true. The sum of degrees always equals two times the number of edges. It's because every edge will contribute 2 to this total sum. And if you don't believe me, you can count them up over here. There's 1, 2, 3, 4, 5, 6 edges. And it is not a coincidence that the sum of degrees is 12, which is 2 times 6. This is always going to be true because every edge adds 2 into this number. And so the sum of degrees is always equal to 2 times the number of edges. Here there were 6 edges, and the sum of degrees is 12. All right? And so that means it has to be even, right? Because it's 2 times something, that automatically makes it even. So it's even. Right? Because 2 times anything makes it even. That's what even means. So the sum of degrees is always even. All right? This is the end of the proof of the sum of degrees theorem. All right. This is like I said last time, very, very strange fact that means weird things about all kinds of real life situations. Like, for instance, it means that on Facebook, for example, I think I said this last time, the number of people on Facebook who have an odd number of friends is even. This is just a weird fact. Why is that true? It has nothing to do with the way friendships works or the way Facebook works, really. It's sort of true because of this sum of degrees theorem. All right? Very weird. I have one more, this is sort of one last real world example where the sum of degrees theorem came up. This, I believe, is a true story, although I've tried to research this. This is a sort of a fun fact that mathematicians like to talk about. A lot of coughing this morning. It's all right. I hope you survive the week. A fun fact that a lot of mathematicians like to talk about, although I've tried to research this and I'm not sure if this is actually true, but we're going to pretend like this is a true story. So this is a true story about the NFL. You will quickly learn as I'm talking about this. I know essentially nothing about the NFL. But this is a story from the NFL's past. The NFL had 26 teams. I don't believe that's true anymore. But at one point in the past, this is the story that the mathematicians like to tell. The NFL had 26 teams, and it's grouped into 2 conferences. And at this time, there were 13 in each conference. And the rules, each year they sort of decide ahead of time how many games they're going to play. And there was one year when they made these rules. The rules say each team should play 11 in-conference games during the season, and then a certain number of out-of-conference games, but whatever. This is what I'm talking about here. Each team should play 11 in-conference games during the season. So in the conference there are 13 teams, and the rules say that they should each play 11 games. These rules were just decided by probably some TV guys about how many games do we want to play this season based on, whatever. How many events do we want to have at these stadiums or something? All right. So somebody decided this would be the rules about the schedule, and then they gave it to somebody else to actually work out. Okay, then what are exactly the 11 different games going to be? So not everybody plays everybody else, because that would be, I guess there are 13 teams. If it said the 13 teams each play 12 games, then everyone would play every other one, and that's how they would do it. But what about to make it so that each of the 13 teams would play 11 games? They gave this to the schedulers, who quickly realized actually this whole arrangement is impossible because of the sum of degrees theorem. It's not obvious when you look at this, but actually this is all, so this rule is impossible. Why is that? It's because if you think of this in terms of a graph, the natural way to think of this graph would be you make a graph where each vertex is a team. And whenever two teams play a game, you put an edge, right? So each vertex is a team, and each edge represents a game between the two teams. All right? So you have, one team is like the Patriots. Brady. He's not there anymore, right? But I grew up in the Boston area, so I know all about the Patriots, which is to say I know what the Patriots is. All right? And they have a bunch of edges representing all of their games. And can anyone say what's the degree of this vertex going to be? It's not the picture that I just wrote. I mean, they have lots of games. What do you think? According to the rules that I set up there? Nobody's coughing now, huh? What do you say? I said each edge represents a game. How many edges are going to be here? The Patriots, I'm asking how many, each of these edges represents one game. So how many should that be?
13.
I don't think it's 13. I said how many games each team is supposed to play. 11. Yeah, each team is supposed to play 11 games in the conference. So the degree here will be 11. Since they should play 11 games, right? But how many of the vertices are there? There's 13 vertices. So this graph will have 13 vertices, each of degree 11. And that is impossible by the sum of degrees theorem because the number of odd degrees in a graph must be even. All right, and this is not true in this graph. Here, they all have odd degree, but there's an odd amount of them. So here, this is impossible. Since we will have 13 odd degree vertices. But the sum of degrees theorem says the number of odd degree vertices must be even. And so those rules are just straight up impossible, and they had to go back and change the rules. It's not possible to make a schedule that obeys those rules that I said before. We'll have 13 odd degree vertices, but this must be even in any graph because of the sum of degrees theorem. All right? So the sum of degrees means that in real life, certain weird things are true. Like, for instance, the number of people on Facebook who have an odd number of friends must be even. And also it means that certain things that seem totally reasonable actually end up being impossible, like this arrangement of scheduling or whatever. All right? It makes you kind of appreciate things like, anybody who makes up complicated schedules like this, like the people who make up schedules at the university or something like that, of classes and who's in what class or whatever, there are actually mathematical graph theory considerations that need to be appreciated in order to make up schedules like that. And certain things are just straight up impossible because of this sum of degrees business. All right, strange but true facts. In my opinion, this is very weird. Great. This is all that I want to say about the sum of degrees theorem. So you'll see some homework problems involving the sum of degrees theorem, and it is one of the things on our list, so we'll have a question on our test about it. All right, let's move on then to the next thing on our list, which is back on the topic of Euler circuits and Euler paths. I would like to talk about actually finding and drawing Euler circuits and paths. All right, finding and drawing Euler circuits and paths. I don't know why I decided this morning to ask ChatGPT to tell me give me a math joke about Euler circuits. You want to hear what it said? This I was not expecting very good results. It said, why did the Euler circuit break up with the graph? And the answer is, the hilarious answer is, because they just weren't really connected. I don't really get it. I think it just used the word connected because it knows connected is sort of a graph theory word. It doesn't make a lot of sense, but yeah, tell your friends. Finding and drawing Euler circuits and paths. All right. Euler circuits are related to graphs, which also are related to the word connected, but they don't really go together in a joke like that. I can't think of a better joke about Euler circuits and paths. But anyway, this is something we talked about before the test, and there was a question on the test about when they exist. So I will just refresh our memory. We know that an Euler circuit exists if all degrees are even. I hope everybody remembers this. And an Euler path exists if all are even, all degrees are even except for two odds, right? And neither exists if there's any more than two odds. And what about if there's only one odd? That's impossible because of the sum of degrees theorem. There can't be only one odd. There has to be an even number of odds. And so that really describes the whole situation. And I hope everybody remembers just what an Euler circuit means. An Euler circuit is one which is a circuit, so it starts and ends at the same point, and it uses every edge without repeating them. To me, a successful math joke about Euler circuits must somehow reference the fact that an Euler circuit doesn't repeat any edges. That's the whole point of an Euler circuit. I begin to question whether ChatGPT actually understands what an Euler circuit is. Although I'm sure it does, it just wasn't able to work that into the joke. All right, so this is what we know about whether or not an Euler circuit exists. The big question, though, that remains is, but how do we find one? This is something that we have not yet talked about. And I did not ask you on the test to actually show me where the Euler circuit is. I just asked you, does it exist or not? So does it exist or not is very easy to answer based on the degrees. Actually showing where it is a more complicated thing, and that's what we're going to talk about for the rest of this time, maybe a little bit next time. How do we find one? There is a procedure for drawing an Euler circuit that will always lead you to the right answer, although it's a little, I don't know, in my opinion, it's a little confusing to do this out. But there is a, can I say, an algorithm. This is a fancy word for just like some kind of procedure to solve usually some kind of mathematical problem. There is an algorithm, and it has a person's name on it. This is called Fleury's algorithm. And Fleury's algorithm, that I think is a French guy's name. Fleury's algorithm is a method by which you can draw an Euler circuit or Euler path. It works for either one. You just have to know. You have to know, how to do it. The details of it. What is it based on? Fleury's algorithm is based on a simple idea that we haven't really talked about. It's based on looking at what are called bridges in a graph. And what that means is, so here's an example of a graph. This is kind of a long chain. All right, say that's a graph. A bridge is some of those edges there. Some of them are bridges and some of them are not bridges. A bridge is an edge whose removal makes the graph disconnected. All right, and I hope everybody remembers what disconnected means. It means like the whole graph is like in two separate pieces, two separate chunks. Technically speaking, disconnected means there's some pair of vertices where you can't get from one to the other by following edges in a path. So a bridge is an edge whose removal makes the graph disconnected. I can see a bridge like right here. This edge in this graph is a bridge, because if I were to take that edge away, then the whole graph ends up being just two separate pieces, and that is disconnected. So this edge right here, this is a bridge. That's because if I were to remove that edge, then the whole graph would be in two separate pieces. Are there anybody see, are there any other bridges in this graph? Other edges where when you remove them, it makes the graph disconnected? Are there others? Maybe I'll say this right here, this is not a bridge. Because if you take that one away, the whole graph is still like in one big piece. It looks kind of weird. This is no longer a square. Now it would be like just those guys would remain. But the whole graph is still connected in one piece. So that one is not a bridge. Anyone see another one which is a bridge? The one, what?
Next to the chart.
Yeah, next to the first one that I said, this one right here. Yeah, that one is also a bridge. If I take that one out, the whole thing becomes disconnected. I can see two other bridges. Anybody see another one? Yeah?
All the way to the right?
All the way to the right. Yeah, actually both of these are bridges. This one right here, if you take that out, then what will remain is this lonely guy over here, which will be disconnected. And also this one is a little, I don't know, you just have to be paying close attention. But if I remove this bridge, if I remove this edge, I will have one lonely vertex with no edges on it, and that also counts as being disconnected. So even an edge which has only one guy on its end, that is automatically a bridge, because this vertex will be disconnected if I take them out. All right, but all of the other edges in this graph are not bridges, because you could take them out and the whole thing would still be connected. Okay, a bridge is an edge whose removal makes the graph disconnected. And now I'll tell you how to do Fleury's algorithm. Fleury's algorithm. It says, this is the procedure to find an Euler circuit. And we'll talk about paths in a moment. It's really the same thing for paths, but there's just a slight technicality. To find an Euler circuit, you start wherever you like, and you choose, the circuit starts somewhere and then it just sort of goes around inside the graph. You should choose edges one by one to decide where to go next. So you choose any sequence of edges. Some people have a hard time with this because actually most answers will be correct, and there are many possible correct answers, which means you'll just have to sort of make it up as you go along, which some people don't like to do in a math class, but that's how most of mathematics is really. You choose any sequence of edges, but, and here's the thing about bridges, be sure to never choose a bridge among the set of unused edges. And this is the part that I said is actually kind of a little tricky to do. Never choose a bridge among the set of unused edges. All right, and I'll try to say what I mean by that in a moment. But this is Fleury's algorithm. And if you do everything correctly, if you do it right, you will end up where you started. In an Euler circuit. So when you're doing this procedure, actually, you don't really have to think about trying to use every edge without repeating any. If you follow the procedure about bridges and whatever, it will just naturally happen that you will automatically make an Euler circuit in your graph. All right. So I got an example to try, and then I have one for you all to try. Let's try this here graph. Now, once you get good at this, you can kind of do this all sort of in your head. But at least for now, I'm going to try to explain every last step of the way. It'll probably take me several minutes to talk through this example, where if you know what you're doing, you can do this sort of in just a few seconds probably. Anyway, here's my graph. Let's find an Euler circuit. All right. So first you should just make sure that the degrees are appropriate so that it actually exists. If I were to look at the degrees, that's a 2, that's a 4, this is a 4, that's a 2, that's a 2, that's a 4. So they are all even, which means yes, there is an Euler circuit, which is good news if I ask you to find an Euler circuit. There is an Euler circuit because they're all even. How do you actually find it? So let's do the procedure that I said. First of all, I said you can start wherever you want. I'm going to start here. Just chosen at random. You can choose any starting point that you like. And then I said the procedure is, let me just refresh our memory. It says, choose any sequence of edges. Be sure to never choose a bridge among the set of unused edges. So as I go, I'm going to try to hold in my mind, what does the set of unused edges look like? Now, at this point, I haven't used anything, and so the unused edges are just everything, right? Everything is unused. So from here, I have two choices. I could either use the diagonal or go straight up, and I said you can just choose whichever one you like. Now, for the sake of us all doing this together, let's all make the same choice. Let's take the diagonal here. But really, you could have started in either direction. I'm going to take the diagonal. And as I draw this, you will notice my line that I'm drawing is not on the edge, but slightly next to the edge. It's because, hear me now, believe me later, if you draw your lines right on the edges, it will be impossible to read after the fact. I'll show you what I mean. But anyway, this is how I'm going to begin, all right? So I chose that edge first. Now, I am again thinking about my next choice. Now I have actually three different options, right? What your job is, you must choose one which does not make a bridge among the unused edges. So what I'm sort of holding in my mind, and this is not so hard to do in your head if you know what you're doing, but if it's your first time, it's a little tricky. But what you do is think of the unused at this point. At this point, the unused looks like that, right? I used that diagonal one, but everything else is unused at this point. Maybe I'll make this a little less crazy. Okay, so I'm here. I need to choose one of these three options, and the rule is you cannot choose one which is a bridge in this graph. Now, this graph at this point doesn't have bridges except for that, right? The only bridge here, I suppose, is this one, but I'm not going to choose that one anyway. So actually here, we can choose any of those three directions. We have at this point three good options. Three good options. And again, just so that we're all on the same page, I'm going to pick the one that goes across to the right. So let's take that one. So my line here is going to go like that. And again, I drew my line there so that it does not exactly go along the edge and also does not hit the vertex. This is important. If you draw your line so that it goes all the way to the vertex, this is a little artistic thing. See, I kind of indicate that this is where I'm going, but I didn't actually draw my line into the vertex. It's because if you draw your line into the vertex, it will be impossible to read the answer after the fact. All right, anyway, I now chose that one. All right, next. So now, at this point, the unused looks like, oops, not that one anymore. Here, it looks like that, right? Where I am now here. And now, this one going down is now a bridge, so I should not use that one going down. Because, I mean, the idea is, if you used this one going down, you would then be stuck here and you would never have an opportunity to cover these other ones. So, don't go there, because that's a bridge. You should instead either go straight up or go up the diagonal. And the way I did this on my paper, I went up the diagonal. So let's go up the diagonal next. All right. Like I said before, when you're doing this, if you know what you're doing, you can probably do all of this in your head. But I'm just trying to explain in detail. All right. What does the unused look now? Now, after that third edge, now the unused edges are like this, right? And I am up here. Again, I have three options. I could go straight across or down one of those two directions. Any of those is okay except for the straight across. You should not do the straight across because that is a bridge in this graph, right? Remember, that means that if I were to exclude this edge, it would become two disconnected pieces. So I will instead go, I believe I'll go straight down here, although it doesn't matter. You could go all the way down or just the little guy. I'm going to do the little guy. So from here, I go down the little guy. All right. And now, sorry to be scrolling up and down here. Now the graph which remains looks like this, right? And we are here at this point. And now I think I can see how to just cover everything up without retracing any steps, right? I can go down, back up the side, across the top, and down the edge, and we'll be done. All right. Now just finish them all on a path, right? We can now just cover each of those edges in order, ending up back on the lower right corner here. All right, now we just finish the rest of them on a path. So my final answer, just to finish off here, from here, I'm gonna go down, up this guy around the side, across the top, across the side. And like I said, we magically do end up at the place where we started to begin with. You don't really have to try to finish where you started. If you do everything properly, you will automatically end up where you started. All right. This is the procedure which leads to, This is now an Euler circuit on the graph. It uses every edge exactly once without any repeats. All right. Anybody got questions about this? This is a little tricky. Yes?
I just have a question about like when you're drawing the arrows. When you go around, does it have to be on the outside, or can the line still be on the inside? For when you go like up the top?
Up here?
Yeah. Like, does it matter?
No. I think are you asking like, could you instead have drawn it sort of like that? Yeah, that doesn't matter because my red line is just trying to indicate which edges I'm following.
Okay.
So if it doesn't matter. Yeah, exactly where you draw it. All right. Can I just convince everybody that you really should draw your line slightly sloppy the way that I did? Of course, this is not an art class, and it's okay with me if your picture doesn't look the same. But check it out. every time when I look at people doing this on the homework, somebody wants to be that guy who's like, oh, that's so ugly looking on the left side. Why don't I just follow the arrows exactly? Maybe I'll thick it up a little. Go across that one and then across this one. Doesn't this look a lot nicer? I would say so far it kind of does look nicer. Then you go down, then you go down again. Now I hate it. Anybody else hate it? Now I hate it because it is no longer clear what you're talking about. If you start here, you go up this one, and then what? I can't tell anymore on your picture. Does it go across first or down first? This picture, if I were to continue, let me just finish it off here. Like this, right? This picture gives me no indication of where this path is actually going from one edge to the next. Because you're going right into the vertices, it's impossible for me to tell what you're talking about. So this is, I mean, maybe it looks less messy to you, but this is unreadable. So you don't have to draw your picture exactly like I do, and you can try to beautify your picture to some extent, but if you beautify it so much that I can't tell what you're talking about anymore, then this is a problem in terms of me giving you a grade on these problems. All right, so don't do it like that. Do it more like this. All right. I got one for you all to try. See what you think. Oh, sorry. I was going to. Yeah. Here's one. See what you think. There we go. See if you can draw an Euler circuit. I will leave it up to you to decide everything. So you're going to decide where to start, and then you're also going to decide how to choose each edge going one to the next. See how you feel. I'm going to walk around and see how you're doing. The only thing to keep in mind is never choose a bridge among the unused edges. And draw your path a little sloppy so I can tell what it means.
Oh, yeah.
These arrows should connect one to the next. Really? Okay. You okay here? Looks good so far. How's it going? Can I make an artistic? Each arrow should move right here, for instance. Yeah. This part is not so bad, but like, for instance, or like here, I'm not sure where to go after here. Yeah, so you should, it's not close. All right? Mm-hmm. Can I make an artistic comment? Maybe I've been saying this to everybody. Can I make an artistic comment? I've said this to a few people, but I might as well say it to everyone. When you draw your arrows, some people heeded my my recommendations that it should be sort of next to the edge. So for example, here's a simple example. What if I decided to do like this? Here's what I don't like. I see some people drawing like this, and then this, and then this, and then this, and this, and then this. This is a problem. It's really exactly the same issue as I just said before. It is not clear what happens right here. After doing this edge, does it go straight across or up the diagonal? I have no way of knowing by looking at this picture. So when you draw your arrows one after another, they have to actually connect up to each other. So I would draw something like that to indicate where the curve goes from one arrow to the next. So don't just draw a bunch of disconnected arrows. That is still impossible for me to tell what you're talking about. Your arrows must actually sort of connect to one another in a sequence.
Yeah.
Here.
Yeah.
This one moves on.
So it goes
Back down here. Yeah. All right. How's it going? No, you can't reuse that edge. Do that first. Yes, yeah. I think it's better if you just do this first. And now we go back to there. All right. Uh-huh. Yeah, that's good. How's it going? Where did you start? That could work. Yeah, good work. Good here? Yeah, that's pretty good. I think so. How's it going? You have disconnected arrows that won't work. Like for instance, right here in the middle, for instance, and right in this arrow. Yes, now I can tell. It goes through first. Like from here, what does it go like? Your arrows don't actually connect them up then. Looks good. How's it going then? Yeah, looks good. All right. Mm-hmm. Where did you start? Yeah, this, I think, you have to be on one path. Because of where did you begin? All right, can we talk about this? And then, so everybody's answer is going to look different, but for instance, the way that I started this off is a perfectly fine way to have started. Next, and remember, as you're doing this, what you should be keeping in the back of your mind is, look at all the ones I didn't use look at all the ones I didn't use yet, and make sure they remain connected up with one another, and they really do. If you're ever in a situation where the ones you haven't used are in two separate pieces, then you have a problem. You're not going to be able to make it work. But all of these ones which I haven't covered yet remain connected, and so I am still feeling good. So I started here. Again, you have to draw your lines somehow so that I can tell where you started and where it goes from one to the next. So for me, I'm going up like this, around this triangle here, and now I will continue across the top like this. Some people are asking me about things like, does it matter if I draw my line sort of inside or outside? None of that matters. For instance, you could ask, why did you draw it inside the thing here but then switch to outside here? It doesn't matter. The whole purpose of this line is just to tell you which edges I'm going along. You can draw them sort of to the left of the edge or to the right of the edge or above or below. None of that matters, all right? Okay, from here, where should I go? Can I go across to the middle, down the diagonal, or straight down? Actually, any of those will work. Maybe I'll go across the middle here. And then from here, I have to go down. You can never reuse an edge. Here, I will go up the diagonal. I didn't go off to the left because that would isolate me from the rest of it over here. Up there, down there, and across the bottom, finally. To the end. So this is my Euler circuit. I use every edge one time without repeating any. All right. As I was walking around, people look pretty good. Just make sure that I can actually tell what you're talking about in your drawing. All right, I guess that'll do it. We'll do several more examples with these next time.